All right, in this video, we are going to be determining the global extreme values on a given domain. This is the last problem from assignment 3 in my Calc CD class. And let's take a look at the problem. So this is number 37, and we have f of xy is x cubed minus 2y. X goes from 0 to 1, y also goes from 0 to 1. So we're above the unit square in the xy plane. So I like to start off by graphing these things. So here's what we got. We'll have this. So this is 1, 1, and that's the point 1, 1. So there's actually a couple of things we need to consider. The absolute maximum could occur somewhere along the boundaries of the region, or it could occur within the region. So we have to look at the boundaries, which means we're basically doing the candidates test on 4 different little segments, and you always have to test the endpoints with the candidates test. So no matter what happens, we're going to test 0, 0, 1, 0, 1, 1, and 0, 1. So we are testing those no matter what happens. They're the corners of the region. Now what we need to do, in my opinion, is write parametric equations for the boundaries so that we can sub them into the function and look for critical points along the boundary. So I'm going to label these up. So 1, 2, 3, 4. We don't need to get fancy with this. We can basically always let either x equal t or y equal t. And because we're going from 0 to 1 in all cases, we can just have t go from 0 to 1 in all cases. Doesn't need to be fancy. You don't need to be like going in one continuous loop around the edges. There are 4 completely different problems. So for boundary number 1, I'm going to let x equal t. And then y will always be 0 because you're just on the x-axis. And then t will go from 0 to 1. And I'm going to go around and do that for each of the boundaries. So for 2, for example, I'm going to let x equal 1 and let y equal t. And then if I do that, t will go from 0 to 1 again. For boundary 3, I'm going to let y equal 1 because you're just up at y equals 1. Let x equal t. And I'm going to go from 0 to 1, which means I'm going from left to right, which kind of feels wrong, but it doesn't really matter. This isn't something where the direction in which you're going makes a difference. So I will let x equal t, I will let y equal 1, and I will let t go from 0 to 1. And then for boundary 4, I'm going to let x equal 0 because that's what x equals. And then I'm going to have y equal t. And again, I'm going to go from 0 to 1, which again maybe feels wrong because you're not like going around in a continuous loop. Or maybe you don't care about that. It makes me feel weird to do it, but like it would be overcomplicating to do it any other way. All right, so now what we're going to do is we're going to take our boundaries and we are going to substitute them into f of xy. And then it turns into just like a Calc AB problem. So we have this, Calc 1, Calc AB, whatever you think of it as. So it'll be f of t comma 0, which is just t cubed. So I'm going to find the derivative of this. The notation I always think breaks down a little here, so I'm just going to call it f prime. F prime is just 3t squared. That equals 0 when t equals 0, which means I need to check the point 0, 0. But 0, 0 is one of the endpoints, so like technically it's kind of on the domain, but like not really. I mean, we were checking that anyway, right? That was one of the corners. So nothing new there, but there was a point that we have to consider. Now we will do this one, right? So we're going to do f of 1 comma t. So f of 1 comma t is going to be 1 minus 2t. And then f prime is just negative 2. Negative 2 never equals 0, so there are no critical points. So again, we would have to check the endpoints because we're basically doing the candidates test. But we already listed the definitely check these points on the previous page, so we already are checking those. 3. X is t, y is 1, so we're going to do f of t comma 1, which should give me t cubed minus 2. So t cubed minus 2. The derivative of that is 3t squared. So f prime 3t squared, which equals 0 when t equals 0. So if t is equal to 0, then y is always 1. So we get the point 0, 1, which we were already checking, but we did get it. So that's good. And then for the 4th boundary, we have x is 0, y is t, which will give us f of 0t, which is negative 2t. which has f prime negative 2, which is never equal to 0. So in this process, I would say almost all the time when you do this process, you just do not usually pick up extra critical points. That doesn't need to be the case. Like, you could pick them up, they just like don't, in a lot of examples. I think you'd have to, as a problem writer, you'd have to work very hard for there to be a critical point that really makes a difference here. But, I've always said that I should search out a lot of examples like that just so, we have them, but I've never taken the time because I have to do every single problem to see if it happens. And that seems kind of miserable. All right, so we got no new points here, but we already had all the points we were going to check. And what if there's a critical point within the region where a minimum or a maximum might happen, right? Think about like a trampoline, I guess, or I don't know, just like a piece of fabric that you're just like putting over this square frame and then the fabric's going to like droop down. The minimum could definitely be within this region. So I have to look for critical points within the region. So I'm going to find partial x, I'm going to find partial y, and if you're thinking ahead, you will notice we are not going to get any critical points because partial x is 3x squared, partial y is -2, which, as we have seen many times, is not equal to 0. So there are no critical points because any critical point would need to have y equals 0, or partial y equals 0, and it never does. So that's not fun. So there are no critical points. So I don't know. This is like the only example that I chose to do in this problem set, and it just doesn't have them. But it's a lot of work anyway. So we got to test our points. So the points were 0, 0, 1, 0, 1, 1, 0, 1. If there had been a critical point, we would add that to the list. It's pretty common for there to be critical points within the region. Like, a good problem would definitely have those, but I didn't choose a good problem. So now we just plug it into f of x, y. So 0, 0 gives 0, 1, 0 gives 1, 1, 1 gives -1, and 0, 1 gives -2. And from this, we know the absolute minimum is -2 at 0, 1, and the absolute maximum is 1, and that occurs at 1, 0. So we went through all the steps. I apologize that there aren't more interesting things happening, but with interesting things tend to come interesting, more complicated work. So maybe it's for the best. I don't know. Anyway, I hope this was helpful, and good luck.